Okay, cool. Yeah, I will take the clicker. So, very nice from Alberto to give a little introduction to containers in HPC before my talk. So thanks, Brian, for making this happen. That's awesome. I'm going to talk about the HPC Container Conformance project, which came out of the HPC Container Advisory Council that is run by CJ from NVIDIA. It's an online meeting that we have every first Thursday of the month. And in October or so, we discussed that we need to figure out a way to make expected container behavior and also annotations and how to build images, that we need to create a project that tries to deliver best practices and some guidance on how to build containers for HPC. And that's where this HPC Container Conformance project, which the name grew on me. I had for a lack of a better title in this slide before, but the last couple of months I think I will stick with this project name anyhow. So containers are here and they are going to stay here, right? So and since Alberto already gave the introduction or an introduction to containers in HPC, I don't need to talk about it too much. But maybe in case you missed it, the Perlmutter system uses container or used container to do the LinPack benchmark, which just shows that it's at scale also possible to run containers in HPC, just as a side note. The problem, or I should say challenges, I think, is that people are used to pick the right binary for the underlying system by module load, right? It was configured by the system admin to pick the right binary for the underlying system. So if you're on Skylake, you will get the binary, the GROMACS binary from this system, and it's a decision that it's made at runtime. So you submit a job, you do module load within the job script, and off you go, you get the best binary for the job. With containers, it's a little bit different because containers should be small, they should be nimble, and they should be maybe only optimized for one single target. So you need to deal with this lack of runtime decisions that you can make. So I think a lot of sites, a lot of customers or users, they create a naming scheme that they come up with on their system, on their site, which then encapsulates the information for which target the binary or the container is built in the name. So you have maybe a Graviton 2 image for GROMACS, a Skylake 1, a Zen 3, or maybe one that is targeted to a specific cluster without using the name of the CPU, but just the cluster name. And this, of course, causes a lot of problems, because if you submit a job and you do not know which instance you are going to run on, you cannot submit one of those jobs because it's then tailored to a specific architecture. So that's kind of messy, and we struggle with this a lot. So we made this project to somehow get around this, right? So what we try to do with this conformance project is we want to collect a lot of ways to how sites building containers as of today, and then use this to derive best practices on how the container should behave, how it should be built, and finally, and that's the most important part maybe, how to annotate a container. And I will talk about labels and annotations in case you do not know what the annotation of containers is. And then create, as I said, best practices and annotations not only for the end user but also for the sysadmin, how to configure the system to make best use of the container in the end. And a side effect is also going to be that we can create some expectation management in terms of performance and portability, because we have annotations, we have metadata for the container that will tell you something about what the actual performance is going to be. We set out to use two applications, GROMACS and PyTorch, eventually WRF, but we will start with GROMACS and PyTorch. And as I said, go through the exercise of creating this best practice and annotations for those containers. What we are not going to do, of course, is boil the ocean and make everything work everywhere. That's hubris, so that's not what we are going to do. But we want to allow for generic images also as optimized ones. So if you go and download the official GROMACS image, for instance, it's a generic image. It doesn't have any information that it's like optimized for this and that. but what it does do is it has multiple binaries within the GROMACS image, and at runtime it will do kind of the module load approach of picking the best image depending on where you are at. It has like Skylake image binaries, more generic binaries, and it also carries CUDA with it, so that's where it's very big, right? CUDA is 4 gigabytes of the whole image, and the image itself is 5. So it's a generic image that tries to cater to all needs, and we will try to also include those. But what we actually want to do is have optimized images for a very specific target, and then use annotations to make the expectation clear and for which system this image is going to run. We are going to focus on OCI images, or I'm going to focus on OCI images, and we want to build this mostly with Docker files because, as Alberto also said, that's the way like non-HPC folks use containers, and we don't want to be too HPC specific here because AIML folks maybe also want to use this. And we use Docker and OCI images. And if we create a Docker file out of something else, for instance, a spec YAML file, we want to include the spec environment also as an artifact to the image, or an HPCCM recipe as well. Okay, the first step is going to, like in the first part, I'm going to talk about what we expect of an HPC image, like how should it behave, what's the entry point, what's the command relationship. And then the second part, the bigger part, is how we want to annotate images to inform the end user and the sysadmin, and what kind of annotations we are thinking about. Okay, first, there's a nice container, biocontainer paper, like bioinformatics container paper from 2019, very early, which does a lot of the groundwork, a cool baseline for this project, because it talks about 11 things that are recommendations for packaging and containerizing bioinformatics software. Of course, bioinformatics software does not really care about MPI, does not really care about targeted binaries because it's mostly Python. So there is something that is lacking for the HPC community, but it's a very cool paper. So if you are interested in this topic, I really recommend this paper as well. Okay, let me first talk about expected image behavior. There are two types of containers in some sense. I call them login versus application container. And the application container is a container that uses the application that it's meant to run as an entry point, so you can use it basically as an alias to the application. So for instance, this Go Releaser image uses the entry point Go Releaser, so if you do Docker run and the image name, it is as if you would just execute the binary. All the arguments you add behind Docker run, the commands, they will be added to the application. So it's kind of an alias. It's great for certain use cases if you want to make it very transparent, or like transparent to the user if he's using a container or not. Doesn't matter. But for HPC it's a little bit cumbersome because it hinders to debug the container. If you need to override the entry point in Docker Run or the other clients, it's a little bit cumbersome. I always need to Google how to actually do the entry point piece because it's unintuitive, at least to me. And if you have multiple tools within the container, say you have a pre or post processing step within a different binary, then if the binary is kind of the entry point, you cannot just override it. So I think that's, for HPC, it's not really worth it. So what we want to do, and what most people do anyways, but I just wanted to make this piece here to solidify this and agree on this, is we want kind of lock-in containers. So you execute the container, like Docker run this and that, and it will drop you into a shell, most likely a bash or that shell, whatever. And so this looks and feels as if you would log into an SSH node, a login node, and execute a command, right? And if, as we all know, and I think Alberto had it on a slide as well, you can do MPI run, Saros run, and then just the GMX command afterwards. It's just in addition to the command, and it feels, I think, very natural for people to do this. So the entry point, and the entry point I have in the down there, is the entry point that spec creates within a container. It's just reads a profile that sets up the container to find the binary, in this case GMX, and then you can just execute the command afterwards and it will just work. So I think that's common sense, hopefully. I gave this presentation a couple of times already, and I think there was no opposition to this login container piece. The other thing, of course, what's very important is that we have some expectations of the user ID and the group ID that is used within the container, or usable within the container, if you will, because if we use Ceros Run, if we use it in HPC environments, we need to make sure that the processes are running under the user and group ID of the user that actually wants to execute the process. And so the container itself, the etc passwd, doesn't know about the real username. So you should not have scripts within the container that rely on the actual real username of the user, because the real username is not there. And it also implies that the container needs to be able to not rely on privileges to read certain directories that are maybe owned by root. So the container should be able to run as nobody, essentially. And I think that's also common sense already. Another thing that came out of a discussion earlier is that it would be nice to have some kind of help message as a default command so that we can inform people how to use the container. I think that would be cool. So if you have a GROMACE container, for instance, and you don't specify a command, the entry point will just render maybe a markdown file so that you have kind of a message of the day that shows you how to use the container with a small hello world example. I think that would be cool. And if you don't want to do this, then you just do bash as a command and it will drop you into a shell directly. Okay, that's the first piece. And now the bigger piece is I'm talking about annotations. And for those of you who are not familiar with the container technology, I will talk about annotations and labels in the next couple of slides. If you have questions, just raise your hand or shout and ask questions, because I think if you're new to this, then it's something to digest. Anyhow, so labels might be familiar from Docker files. So you in a Docker file, you can specify labels, which are just key value pairs that are then included into the container image at the end. And how is it done? If you build something, like if you build this Docker file, for instance, it will create a manifest, and the manifest includes all the layers that are part of the image, and also a config blob, a config object, this container image v1. And the actual labels are part of this config object. It's just the JSON blob that has among other things, like what command to be used, what entry point, what environment variables, and so on. It also stores the labels. If we talk about annotations, it's a concept that is now introduced by the OCI image spec. So as we saw before, and I go slightly back here, this is the Docker version, right? The Docker format. If we go to the annotations, we see that this is part of the OCI spec. And annotations can be created when you do like a Podman build, -- annotations. It will create an annotation that is part of the resulting manifest. So as we see, it's OCI image manifest, has the annotations that are created within this build command at the manifest level, and all the labels are still part of the config object. And the config object doesn't know about the annotations because it's two different things, right? So labels are part of the image and nested in the config object, and annotations are part of the OCI spec, and we can attach them to manifest and also to image indexes. And I'll touch on this later in the slide as well. Both should follow the annotation rules. There are a bunch of rules, but the most important piece is there must be strings, key value pairs, and the values can be an empty string, and the keys should follow the reverse domain notation, so like org.opencontainers. whatever. But they don't need to, right? And there are transform ground rules, or some rules that I would like to establish with this project for HPC. So first, as I discussed before, the OCI image manifest format has annotations. If you use Scopio, for instance, to transform it into a Docker format, the annotation is going to be lost. So the first ground rule is that if we have annotations in the manifest, we should also have those in the image config object, because this will stick. I'll click this. This will stick to whatever format you transform your image from. Like you can transform it from OCI to CIF. The config object will be there, even though it's a different format, but the information about labels will stick no matter what transformer you do. The other part is that if you have a reverse domain notation, and I have one here, like the org HPC annotation as a label, then I would propose that within the HPC container conformance project, that if you want to be conformant, then you can take this annotation or this label within the config object and elevate it to an annotation, because it has this reverse domain notation format. And the cool thing, I mean, why differentiate this two? If you want to inspect this annotation and you only have the Docker version, you need to first fetch the manifest, then find the config object, then fetch the config object, and you need to do this for all the images you want to inspect. Whereas if you have the OCI format with the annotation on the highest level, you just need to fetch the manifest, and then you can do you read these annotations without going to the nested object itself. So I think it's a better way for higher level tools, services, registries to inspect images. So that's why we might want to elevate this into higher levels. Another ground rule is that annotations should not contradict the ground truth of the labels in the config object. So if we have the same key, we should have the same value. Otherwise, that's a violation of the truth, right? Because the labels are ground truth, and you cannot just override values in the higher level. And the first conclusion is that we cannot trust annotations in this different formats, so we need to store everything in labels anyways. If they are used like in different, from my personal opinion, we use labels and annotations synonymously, and I think we should call labels with a reverse domain annotation, we should call them annotations, and all the rest are just labels. And they should be all stored as labels, as I have in the first bullet point. But if we store them as both, as labels and annotations, annotations should not contradict what's in the labels. That's the third bullet point. If we have annotations established for multiple images, we can do new things, cool things that they think in the future, like in the next coming months. As I said, we have manifests and we have image indexes, or called manifest list in the old version, which is just a set of manifests that you serve for a certain name. Let's say you have Ubuntu or GROMACS for different architectures, for x86, ARM. They will be served as an image index, and then your runtime can pick one of the images inside. We can use annotations in this case as well to maybe have a sane or a constraint that is applied to all the images within the image index. So if we have the image index for GROMACS in this version, and we have multiple images for different platforms, we can use the annotation in the image index to verify the annotations in manifest. So if you have two images in the same index and they violate the version of the software in the top, then we can detect this on a higher level, and we can make sure that we don't mix up versions of GROMACS under the same name. And then there's another advanced version, but maybe for those of you interested, maybe we can talk about this later, but there's cool new compression algorithm, that standard that is part of, or that's understood by Podman and later versions of Docker, where you have storage optimization capability, so you download the same image or different image with some files that are similar. With that standard compression, you are able to reduce the size of storage that you need, because it will apply some optimization of the storage. So you download twice 2 gigabytes, but at the end, most of the files are the same, and you have a reduced set of storage used. And you can also do lazy loading, but yeah, that's a more advanced case. So maybe we can talk about this in the break. Okay, so this conclusion we already had. C, and if we use image indexes, we use annotations to set constraints for all images within that. I think that would be nice to detect manifests that are not part of that have maybe a version conflict or other things. Okay, that's annotation and labels. And in the next part, I will talk about annotations group. That's the first iteration of annotations we propose here in this project. The first one, of course, is hardware annotations. So it's basically an information about the container content and what the actual application is compiled for. So the first group, as you see, is like CPU target. It can be a generic or a microarchitecture target, similar to what you do when you compile with spec. You can define what you want to optimize for. So if the target is microarchitecture and it's Skylake AVX512, you know, okay, the binaries that are included in this image are optimized for this, and if you want to execute it on an older node, let's say Zen 2, then this will segfold because it's optimized for a Skylake CPU. The second part, of course, is if you have a GPU or CUDA version that is carried with this container, you can also specify the GPU vendor and GPU annotations that talk about like what CUDA version or CUDA API is used, what the architecture that the CUDA is compiled for, so that you, from the outside, can inspect the container before you actually download it. Because like containers might be very big. I think from HPE Cray, if you have the fat developer environment, it's like 30 gigabytes or so. If you download the container and then it segfolds because it's compiled for something else, then that's of course a bummer because you downloaded it. In the case of these annotations, you can just inspect the container beforehand, maybe with a Slurm hook, and then you fail early and you don't need to download the container before you actually know what's inside. So that's the goal of the annotations here. Another one that's very important for us, of course, is MPI and interconnect annotations. So with those annotations, we can inspect from the outside which MPI is used, OpenMPI, MPICH, or Thread MPI, what communication framework is used, what version of MPI, what libfabric ABI is used. And the lowest one, I think, is also very important, and Alberto will talk about this on Wednesday, I think. What portability mode is expected by the container. So if you have most of the containers, they will do an MPI replace, as we saw from Alberto's talk as well, that you have an MPICH version on the host and you have an MPICH version within the container, and you just mount the shared objects from the MPI library within the container, and then it will pick up the best performing MPI for the underlying interconnect. And there's this MPI replace. There's a libfabric inject model where you keep the MPI and you don't override what's in the container. You just add another provider, libfabric provider, to the container, which is a more stable version of the old MPI replace part. Or you maybe have UCI replace, UCX replace, where you take the UCI and UCX and replace it within the container. So that's not talking what's in the container, but it's more informing the runtime and the scheduler how the container expects to be tweaked. How can we use this? Runtimes like Serus and Podman, they actually react to annotations. If you do Serus run ---- MPI, it will just add this annotation that you see here to the container and then trigger this hook. And this hook will, as I said before, will replace the MPI libs and mount the MPI libs into the container. It will also use ldconfig to inspect the binary that is supposed to run and figure out where to mount it, or where to mount it inside of the container. So there's a lot of stuff going on, but it's eventually triggered by this annotation. So if we have an annotation for MPICH, if we have an annotation for Intel MPI, if we have an annotation for OpenMPI, we can use those annotations to trigger the underlying hooks instead of telling the user to do some weird arguments to the run command, because the annotations will just be there in the container. If we have multiple containers for GROMACS, one with OpenMPI, one with MPICH, they will trigger different hooks. And then off we go, and it will just work for the user because it's triggered by the annotations. Then we have, of course, other annotations like system annotations, and that's not a complete list here. But for instance, we could say like the container defines or describes what the glibc version is, what the libc implementation is before that, what Python version is installed, so that it informs the user that maybe create a script. What to expect from the container. It also maybe includes common tools like JQ or wget, so that users know what to expect from the container. And the last part here is maybe a path that is all empty within the container, but already in the path environment variable. So you can just bind mount something into this directory in the container, and then off you go, and it will just work out of the box. The other thing that would be nice is if the container has some requirements or some expectations regarding the host, that you can also include this annotations that maybe define a minimal version of the kernel, ABI or version, or you have maybe expectations what modules are loaded on the host, so that you can also figure out if this constraint or this requirement is met before you download the container again. Then documentation would be nice as well. So like if we have quick start guides or hello world examples encoded maybe within the annotation or as a link, or also documentation on how the Docker file looks like, or the Docker file itself, maybe base 64 encoded, and quick start links, quick start documentation on how to tweak the actual container that is currently inspected here. Okay. That are the groups. As I said, it's not like set in stone, and we will discuss it at ISC as well, and hopefully come to a first set of annotations. How do we annotate? I think as I said, the base image, if the base image has labels or annotations that are already in there, this will be carried over to other subsequent images. So the base image should be annotated first and foremost. The operating system or tools already installed, it could be all in the base image. If someone builds a new image, then application versions, dependencies can also be annotated within the subsequent build. Or after the image is built, we can use things like Crane or Podman, or there are a lot of tools that are able to annotate an image after the fact without actually doing a Docker file, but just do Podman build, and then you can annotate images. Or we can collect the annotations in a subsequent artifact, and I will have a little example afterwards. Ideally, we don't need to teach everyone how to annotate. We should strive to make a TOTS and Canis problem. I think that's something that we constantly revert to. But the idea is that if the build tool like Spec or EasyBuild is going to annotate the container image already, then we don't need to tip it, or we don't need to teach it to all the users if all the tools that they are using annotate in the right way. So that would be cool. And HPC CM, the HPC container maker by NVIDIA, already does some annotations, and I think that's a good way to go. If the tool does it, then the user does not need to think about it. It will just be annotated afterwards. That's a snippet of what I talked about, the external configuration. So for maybe if we have ISV images, then we don't maybe have access to the container, or we're not able to tweak the container and upload it again. So having those collections for certain images, as I said, we start with GROMAX, but for certain applications we could collect different images, have their annotations be written down here, and then we can use this information, this YAML file, parse it, and then figure out what the best image is for the job by looking at those collections here. This is annotation, so this is something that the image has, the container image. Another important tool is that we need to develop, and I had a first step at it, is the system fingerprint tool. So a tool that takes information of the host, the hardware like CPU, GPU, interconnect information, operating system information, and so on, and creates a fingerprint of the system, so that we can then use this as an ingredient. Like we have the system fingerprint, we have the container annotation, and this tool then can create a little smoke test or do a little smoke test, like create the fingerprint, and then if it's pointed to a container on the registry, and can just download the manifest or the config object, like look at the annotations and then do some mix and matching and say, okay, it's green if the performance is expected to be perfect because it's a perfect match. Maybe it's orange if the performance is okay, but not optimal. So maybe, and the percentages of course vary depending on your use case. Or if the container does not work at all because it's segfault, because the binary is compiled for Skylake and you have a Zen2, then it won't work. So it will fail very fast. Or if the performance is so bad that you should not even download the container because you can expect very poor performance. So if we have this tool, that would be cool for like smoke tests before actually downloading the image. Okay, so this is the HPC container conformance project in a nutshell, and I'm good in time. The next part is I want to talk about a practical implementation of this by describing the MetaHub Registry. MetaHub Registry is a project I started 2019 or 18, I think, and recently picked up again, which is an OCI-compliant registry, which takes in the context of the user. So similar, as I said before, the module load approach looks at the system at hand, and then it defines or figures out what the best binary within the software share is and creates the environment variables to pick up this binary. And with containers, we have the problem that the registry is kind of a dumb thing because it just has JSON objects and layers, and it's not really taking the context of the user into account. And what I'm doing with MetaHub is I use a profile, maybe the CPU like Zen 2 or Skylake, and I take this context into account when I deliver an image to the user. So we see the collection on the right-hand side, and with the profiles, you define some rules. So in this case, the first rule is I want Linux. Okay, that's of course something that everyone, like the most containers are Linux anyways. And the second one is just a rule that says I don't want optimized images for this because it's a generic profile that just should not rely on a specific target, but just serve the generic images. So what it's going to do is it will exclude all the images with annotations that specify a microarchitecture or an optimization, and it will serve the images that are up here, like the generic ARM image and the generic x86 image. If we put this up a notch, then I have a profile that is for G5 instances on AWS. It asks for this x86 64v3 optimization because it has a Zen 2, and it also wants a NVIDIA, like a CUDA version within the container. So if I use this profile and log in with this profile, then it will just pick the lowest image on the bottom there and will serve this image. Another thing that this collections can do, and I talked about it before, if we have, for instance, a biocontainer image, biocontainer being the registry for most of the bioinformatics containers, which is mostly Python or some Lua, they don't have any x86 ARM images in their stack, and I have an M1 here, so I need an ARM image. And if I do the straight biocontainer image, then you can see that it complains about this being an x86 version. You have a host that is ARM, and all the libraries within the image are also x86, so the performance is going to be poor. If I'm using MetaHub and ask for the same image, just with a MetaHub registry in front, it will serve me the lower image because it will, it has two options, x86 and ARM, and it will serve the best for the actual host. There's a front end as well where you can see all the different images for the GROMACS in this case, and it shows you how to download it. And how does it help? The MetaHub collection creates lists of images for the same application, say GROMACS or OpenFOAM or PyTorch, and we can use this information to pick the best image for the job. Using the annotations that are defined within the image and within the collection, we can then discover the best images for a given use case. And the registry helps with it by having profiles as well. And with profiles, we can have different variants for different nodes or use cases or environments. So say you want an application for the node with this CPU, you can log in with a CPU profile and it will serve you the best image for that. You can also maybe have different images for different environments. So if you are on a laptop and you ask for the GROMACS image, you want the laptop version, and maybe you are less constrained in terms of security because you're running on your laptop. If you're logging in with a profile for a specific production environment, you might get a different image that is also scrutinized and has some security stamp on it. The registry, since it unpacks the manifest and reassembles them, you can also tweak the container. Maybe you want an additional set of files, you want a new entry point, environment variable. All of the things that constitute the container can be changed at the MetaHub registry level and can cater to the right use case. And this makes the registry much smarter, right? Because now it's just a blob store for JSON files and objects like layers. And MetaHub is smarter because it has rules and it can apply changes and manipulations to images. So this one, for instance, I had implemented, but I need to re-implement, is you can specify a manipulation in your profile. Say you have a generic bioinformatics image that does not know about the execution environment. If you use a profile that is maybe an AWS profile, you can add the manipulation to include the AWS command line interface into the container, or maybe you need a certain config file, or you need a license file. The registry can just on the fly add this to the container while it's downloading, and this can be done by manipulations in MetaHub as well. Another one is that if we don't want to include the file on all the images because they are all external, different registries, we can add this help message maybe at the collection level as well, so that it will apply to all the subsequent images. And the other one is collection push. So let's say you're on a host, you want to have a GROMACS image, and the registry says, okay, for your special profile, for your Skylake profile, I don't have an image yet. What you can do is you can log in with the profile you want an image for, you build the image, and then you push it with the profile, and then it will magically be added to the collection in the registry. And the next time you download the image for your Skylake, then you will have it, because it will just be added to the collection dynamically. Okay, maybe I do, because I connected with my laptop for a reason. I have a little demo here. So this is the MetaHub front-end website. I have like different versions here. Let's say we go for the TMPI image. You can see that there are different images for different profiles. We have a generic image, or two actually, for ARM and AMD, and one for G5 instances. Here I'm on a G5 node on AWS, the G5 4XL. If I'm logging in without any special profile and running this GROMACS run, this will just download the container that is in generic, so the upper one, so it's optimized for x86 64v2. So it will complain, and you can see it here as well, it will complain that it's not optimized for the CPU, then it will start running. And maybe you can quit this already. Because I just downloaded an image with a generic profile. I think it needs to start before I can stop it. Here we go. And next I'm going to log in with the G5 profile, which we can see here, like this one. This is optimized for v3, and it has CUDA in it. So once this is finished, "80 steps, okay. Eventually, here we go. So now I'm logging in with node AWS G5, doing the same exact command as before. And now we can see it's using a different binary because it's a different image, and it selected the GPU as well. And it also does not complain about the CPU optimization because it's optimized for the exact host CPU here. I can keep this running, I suppose. That's the first one, and just a little demo as well about the container push. So this is a local version, and what I wanted to show is the collection push here. So if I do this, so here I'm logging in as a generic user again without a profile, and I'm using Scopio to copy the Alpine 362 to the Alpine Lugano name. If I'm reloading this, we can see now I have Alpine, Lugano, and it's a generic profile. Of course, it's an ARM thing because I'm on an ARM system. If I'm doing the same with the CPU Zen 3 profile, it's going to add this profile here, and I have like two different versions, one with Zen, one with generic, and the Zen one is a 17.1 317.1 Alpine. If I do now run with different profiles, the first one logs in again as a generic user, and I have the version 362. If I log in with the Zen 3 profile, I get the 371 image. So they are different images, even though I'm using the same name. And that's the basic idea, right? So you can push and pull images based on a profile that defines certain rules that you want to apply. Okay, I think that's even the demo. Let me switch back here. If you want to know more, there is IC 23 around. We have Friends of Container Boat Trip on the 23rd of May. So if you are interested in container forks, last year we had 30 people. It was pretty nice having a little boat trip through the harbor. Of course, when we entered the container port, then everyone was lighting up, and the guide was like looking weird because before we were very quiet, and then we went into the container port and everyone was cheering, so I needed to explain to her that we are container guys anyhow. And then there is an HPC container workshop on Thursday at the ISC. It's a half-day workshop, and we are going to talk about HPC, this project, the HPC Container Conformance project. And we also have some industry folks to talk about their challenges, because last year we figured that this needs more prominent voice in our workshop, because we are talking about academic codes that we can compile ourselves, and I think we need also to include more of the ISV folks that has more constraints, because they get the code from a vendor, and they need to deal with this as well. So these are the two things. There are more information on containeranhpc.org if you want to join and you want to have more information. That's a demo I already did. And with that, I'm like 15 minutes early, so I think that's totally fine. It's the last call. There is a Slack for HPC containers if you like to join. We have like a couple of hundred people there already, and there's a podcast about container, about myself that I recently did. So if you have any questions, reach out or maybe ask questions now. And I'll stick around for like tomorrow and Wednesday as well, so if you need more coffee, that's fine. No questions? Okay, cool, thanks.